All right, we're in the erratic motion section of the book, and this is section 12.3. And I wanted to do some updates on the S&T, V&T, and A&T graphs and how we're going to utilize those. So you already have a lecture video, but hopefully this is going to focus in on these types of graphs. So the S&T graph is a position versus time graph. And remember that velocity is the derivative with respect to s with respect to time. And if I have a constant velocity, the S&T makes sense that the slope is going to be the velocity of an S&T graph. So remember, this is position versus time, and we're looking at a graph. So let's say we have a particle that's going to travel along this weird curve, and we can look at that position versus time graph and get a lot of information out of it. For example, if we look at this point here at, this along the line 1 and along the line 2, we can tell you that this particle is moving along a straight line, so it's traveling at a constant velocity, and we know that the average of that constant velocity would be the slope of that straight line. We also know that if I go to a point A and look at any tangent on the curve, the slope of that tangent is going to give me an instantaneous velocity. So we can do the similar thing with our velocity versus time graph, or that VT graph, and we know that the velocity versus time, the slope of the graph is going to be acceleration. And if I have a straight line, I'm going to have a constant acceleration. If I'm doing that tangent, I'm going to have an instantaneous acceleration. But my velocity versus time graph is also going to give me some additional information. For example, we know that if we integrate, that's the area under the curve. And when in the other videos that you'll see, we'll look at different rules that we can actually use our curves to be able to get areas under the curve that sometimes when integration isn't necessarily as easy to do. So we can look at this area under curve. So my change in position is going to be related to the area under the curve, and we're going to evaluate our integral from 0 to time t1, which is going to give us this pink area here, and that's our velocity versus time. Similarly, we can do an A&T graph, and we can use that area under the A&T graph to give me my change in velocity is going to be equal to that area under the A&T graph. We can also have velocity versus position graphs and acceleration versus position graphs. And if we look at this and we look at that area under the A and S one, and we look at how we evaluate that integral, we're going to see something that's very familiar from kinematics. So if you remember that one of our primary toolkit questions that toolkit equations that we had is our v squared final is equal to our v squared initial plus 2ax, where a was my acceleration. And of course we did this as a special case where a was a constant acceleration, but I wanted you to see where that would come from if we were doing an acceleration versus position graph. You can see it easily comes from that particular aspect. So we want to, and then of course we can do another way to look at acceleration is the velocity times the slope of the velocity versus position graph, and we can get it there. So I'm going to explore this a little bit, and we're going to use this velocity versus time graph to describe the motion of a dragster. And we've got a nice kind of a triangular, and if you think of a dragster, we're going to try to do a constant acceleration and then have a constant deceleration. And we've got this graph here, and we're told that this line starts as the velocity is equal to 30 times the time, and we're told that this line looks like a negative 15 times the time plus 125, and these are of course in meters per second. So one of the things that we can do with the graph is we can automatically look at what the maximum velocity is. Our maximum velocity, we're told, is 150 because that's where the peak of this motion comes from. So a lot of times you can look at the question. Now we want to construct a position versus time graph using the information that's given to us in our velocity versus time graph. So we're going to have to break it up into two parts. We're going to have to look at that 0 to 5 second interval and that 5 to 15 second interval. So remember that my change in position divided by the change in time is going to give me my velocity. I can rearrange it so I can actually do an integral. And we're going to look at the limits of this integral. So looking at those boundary conditions is very, very important. So I'm starting from time is equal to or is greater than 0 and it's less than or equal to 5 seconds. So I have my boundary conditions for this integral on that side, and then I can do my integration, and then I can evaluate it. And at 5 seconds, we're going to be at 375 meters. I'll do the exact same thing for the greater than 5 seconds to the 15 seconds, but this time I've got to set my boundary conditions from my initial start point at 5 seconds, which is the 375 meters, and I'm going from 5 to 15 seconds. So as we work through that, I can actually work through the gory detail of that integral, and I come up with that the change in position, that S for the total position where we're at is going to equal 125 meters. And now I can plot my S versus T graph. So I've done that. I've gone from 375 to my 5 seconds and to my 125 seconds, and we've got a position D graph. But remember, what we also said is that my change in position is also the area under the curve of a velocity versus position graph. And when I do that, I can really do this really quickly. I don't necessarily have to go through all of this integration up here. I can calculate the area under this one because it's a straight line. It's relatively straightforward. It's 175 meters. I can do it under area 2. It's 750 meters. I add the two areas and I get 525 meters. So I can get the exact same results by doing it two different ways. One by using the graph that it's given me, and the other by going ahead and carrying out the integration for that particular motion. So this is one of the reasons why we want to do that reflect and rethink, because there's usually more than one approach as to how we deal with the problem.